The Josephus problem originates from the 1st century when a group of 41 Jewish soldiers were gathered together in a cave by the Roman army. The Roman army had captured them and made them sit all in a circle. They were waiting for them to be killed, but instead of trying to be captured, the Jewish soldiers rather die themselves and kill each other. So one by one, they decided that each person to their left was going to be killed. So let's say there was 41 soldiers in the circle. The first person kills the second person, and then the third person kills the fourth person, and so on until there's only one person left. That last person that is standing would have to kill themselves by suicide. All of the 41 soldiers agreed that this would be the easiest way to die instead of being captured. All but one soldier. Josephus, one of the Jewish soldiers, rather be captured than die by suicide, but was way too honorable to say this to the rest of the soldiers. So he had to figure out a way to find out which best position to sit in order to be the last one standing so that he could be captured and not kill himself. 41 soldiers were sitting in the circle, and Josephus finally figured out which position to sit in to be the last one standing and not die. This is where the problem originates. The problem's name obviously comes from that one soldier that did not want to die by suicide, but that rather be captured. And then it became a mathematical and computer science problem and actually a counting out game. The game basically is that everyone sits in a circle and you have to figure out which position to sit in order to be the last one standing. The problem with 41 soldiers is extremely long and complicated to do, so mathematical and computer science experts decided to split it in either 11 soldiers or 12 soldiers to explain the even and odd variables of the game. The variables are only two. There's n and then there's k. The n is the number of people, so either usually 12 or 11, and it can go up to any number that the people choose. And k is the number of people that are being skipped each time.
Okay, so here I'm just going to show an example of what would happen if we had 7 people standing in a circle and see how the problem would play out. We always start with player number 1 and we go in clockwise. So here 1 would kill 2, and the next living person is 3. So 3 would kill 4, and the next living person is 5, so they would kill 6, and then finally 7 would kill 1. That is round 1, and then we continue with round 2, where 3 would kill 5, and then finally 7 would kill 3. 1 dies in the first round, but in contrast, if we only had 6 people standing in the circle and did it again with starting with 1 again, 1 kills 2, 3 kills 4, 5 kills 6, 1 stays alive in round 1 and then would die only later on.
So first we're just going to begin with our first variable. So here k is equal to 2 because that's the number of people we skip each time. The second person is the one who's killed in the most basic version of the Josephus problem. So k is equal to 2 because every second person is killed. So this would mean that in the first round, every even person is killed. Let's say we have 4 people. 1 would kill 2, then 3 would kill 4, so each even person. So basically, and then in the second round, since we would only have 1 and 3 left, the odd numbers, 1 and 3 will have technically switched spots. I mean, 1 would remain in the same spot, but 3 would now be in the second spot. So basically, since they alternate spots, there's actually a formula to find out what spot they were initially in. This formula being 2x minus 1, and we're just going to do a quick example to show you guys this works. So let's say we had 1, 2, 3, and 4. As I said, 1 would kill 2, and then 3 would kill 4. And then 1 remains in the first position, but 3 is now in the second position. So to find out where it initially was, we apply our formula and plug in 3. So and plug in 2 because it's now in the second position. So we would do 2 times 2 minus 1, 4 minus 1, 3. 3 is initially in the third position. So that's how we figure that out. So now we can come up with a formula to denote who will be in the winning spot. So let's call this formula f of g. So basically here we're gonna have the formula f of g, and then we're gonna have another formula for n. So n is the number of people that we have in the problem. Let's say here that n is equal to 2g. So basically we're gonna use these numbers, these variables, and sub them into our equation 2x minus 1. So here if we had f of 2g, since that's the number of people that we now have, the person in the winning spot, 2x minus 1, was originally in spot 2 f of g minus 1. So this is what we have right here. But this example only applies when we have an even number of people in the circle. It'll be very different when we actually have an odd number of people, because now in the first round, as Melina explained prior, we end up killing the first person, which messes up the whole order. So instead of using our 2x minus 1 formula, we have our 2x plus 1 formula, since it's one person off this time. So this is the formula that would give us. But the problem is that we probably do want to have one simple formula for all numbers, whether they are odd or even, rather than having to apply different formulas in different cases. So let's try and find a main formula for the whole problem in general. So to do this, we're just going to look at a few examples. So let's just do some examples. So let's say we begin with, I'm just going to do a whole table here of a lot of examples after, but I'm going to show you the first few so you can see the pattern at the beginning on the bottom. So let's say we had, in this example, most basic example, one person. The winning spot is obviously person in number 1. Let's say we do 2 people. 1 would kill 2, 1 wins. Let's say we did 3 people. 1, 2, 3. 1 would kill 2, 3 would kill 1, 3 wins. Let's say we did 4 people. 1, 2, 3, 4. This is the example we did. 1 kills 2, 3 kills 4, 1 kills 3, 1 wins. Let's say we did 5 people. 1 would kill 2, 3 would kill 4, 5 would kill 1, 3 would kill 5, 3 is the winner. Let's say we now did 6 people. 1, 2, 3, 4, 5, 6. 1 would kill 2, 3 would kill 4, 5 would kill 6, 1 would kill 3, 5 would kill 1, and we're left with 5. So basically, these are the first few examples. And if we were to continue, we could come up with a general table. Basically, let's say we had 1 at the beginning. So this would be n, so the amount of people. And then this is our f of n, which is who's going to win. So basically, in the first one, we saw 1, 1. Then in the second example, when there's 2 people, we see 1 wins. In the third example, where there's 3 people, we see the third wins. In the fourth example, where there is 4 people, we see the first wins. In the fifth example, we see that the third wins. In the sixth example, we see that the fifth wins. Now I'm just going to continue over here just for the sake of having more space. So this is as far as we went with our examples, but we could have continued further. So if we were to continue, we would have had, let's go up to 12. So if we were to continue after this, for the numbers, we would have 7, 1, 3, 5, 7, 9. So obviously these numbers are not something you can just guess. These are done from doing the example, and yeah, but I'm just not going to do every single one with 12 people with you guys because that would just take too much time. But if you were to do them and you were curious, you would get these numbers. So now we're just going to look at these numbers and try to find the pattern to be able to come up with one general rule for the problem. So basically, if we take a look at it, we kind of see that the number 1 comes back every so often. So we have 1 here, 1 here, 1 here. So if we are to look at this, we can actually observe that every single number where there's 1 is actually initially a power of 2. So 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, and so on. We can assume that this would happen once again at 16 because of this rule. So basically, first of all, we're going to observe that any number of n, which is 2 to the power of anything, will actually give us 1 for f of n. So the winning position in any of these cases would be 1. So then we can observe that, so f of n, this is how we come up with this. F of n is equal to 1 if n is equal to 2 exponent m, which is 2 exponent anything. Now we can look at this further and try and develop a solution for all the numbers that are not powers of 2 directly. So basically we're going to end up coming up with this rule. So if n is equal to 2 of m plus anything, so basically if n is 2 to the power of anything, you can add a constant. So here 3, for example, is 2 to the power of 1 plus 1. 5 is 2 to the power of 2 plus 1, 6 is 2 to the power of 2 plus 2. So you can basically do this for all these numbers, and that the constant we're adding is smaller than the 2 to the power of something, so then the first number. So for example, let's say 9. 9 is equal to 2 to the power of 3 plus 1. So in this case, our constant 1 is smaller than the 2 to the m, which is 8. 8 is bigger than 1. So this works, this matches our condition. Then so to end, we just wanted to show you guys that the formula actually does work with all of these values. So let's try doing it with 11 and 12, since those are the biggest numbers, which people tend to find scariest. And it's also a good examples to use because this one is odd, while this one is even. So we can see that it actually does work in all types of numbers. So if you take our formula here, it involves having the constant. So let's just decompose these in advance. So 11 is equal to 2 to the power of 3 plus 3. So 8 plus 3, while 12 is equal to 2 to the power of 3 plus 4. So now let's start with our 11. So if we take our formula, f of 11 is equal to 2 times the constant z, so 3 plus 1, which gives us 7, which is once again what we found here. So that works out. And then if we are to do the same thing with the 12, we have our f of 12 is equal to 2 times our constant z, which is 4 in this case, plus 1. And obviously it is going to give us 9, which is what we had here. So this formula tends to always work, and you can apply it in the Josephus problem whenever k is equal to 2. Thank you.
So another way that you can solve the Josephus problem is by using binary. The way that we're going to do that is, so let's say that we start with the number 41, okay, 41. First thing that we're going to do is convert this into a sum of powers of 2. The way that I usually do that is I take a calculator and I will just like test out powers of 2 until I find the biggest power of 2 that would fit into 41 without surpassing 41. So in this case, it is 2 to the power of 5, which is 32. If I were to put 2 to the power of 6, it would have surpassed 41, right? It would have been 64, I believe. So first thing that we have is 2 to the power of 5. Next, 41 minus 32 is 9. So the highest power of 2 that would fit into 9 would be 2 to the power of 3, which is 8. If I put 2 to the power of 4, it would be 16, I believe, which would have been too much. So 2 to the power of 3 is our next one. And then we just need 1. And 1 is just 2 to the power of 0. So once we've written out our number as a sum of powers of 2, next up, we take the highest power of 2 in the equation, write that down, and then we're basically just going to list off every other power of 2 that is smaller than that. Like, for example, we have 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. So we just write out all the powers of 2 that come below 2 to the power of 5. Next up, we write underneath how many of each of these powers of 2 fit into 41, like make up 41. So we have 1, 2 to the power of 5. We have 0, 2 to the power of 4s. We have 1, 2 to the power of 3. We have 0, 2 to the power of 2s. We have 0, 2 to the power of 1s, and 1, 2 to the power of 0. So now we have 41 written in binary notation. Next, the way that we are going to find out which numbered seat is the winning seat, the way we're going to solve the Josephus problem all we have to do is take the first number here, this first one, and just put it at the end of our number, okay? So I'm gonna rewrite that out like that. So 0, 1, 0, 0, 1, 1. Next, I am just gonna go through and write down this equation with these powers of 2. So there's 1, 2 to the power of 0. There's 1, 2 to the power of 1. 2 to the power of 1. And there is 1, 2 to the power of 4. So 2 to the power of 4. That is going to be equal to 19. So if I did the math correctly, 19 should be the seat that Josephus would sit in order to not die, to be the last one to be killed. So I'm going to test that out right now. I am just going to write down, draw a circle of people, 41 people. Okay, so I have drawn out 41 people now. So here's the first person. He's gonna kill this person. Next living person kills this person, and so on and so forth. Right off the bat, we know that all the even numbers are going to be dead right away. That is why your binary notation of the winning seat is always going to end in a 1, because that would make it an odd number. It's always going to be an odd number. Next, this guy kills him, this guy kills him, this one kills him, this one kills him. Okay, so our last man standing is him. Let's count that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. This was the 19th seat, and that is what we got when we did the calculations. So that is right, and that's going to work with every single number. So even if the number was like 16, for example, which would only be 1 power of 2, it would be 2 to the power of 4. Let me just double check that. Mm-hmm. Yeah. Even if we did that, if it was 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 1, 2 to the power of 0, 0, 0, 0, 0. Take the first number, put it at the end, 0, 0, 0, 0, 1. That would just be 2 to the power of 0, which would equal 1. If we worked that out, that would mean that the first person in the circle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The first person in the circle should be the one who survives. So let's try that out. Yep. And there you go. So that is how to solve the Josephus problem using binary notation.